Well, then let's. Our next speaker is Marcos Guimarães, and he will talk about spin-orbit torques using layered materials. Please, Marcos.
No, yeah, okay. Oh, thank you. First of all, would like to thank for the invitation. I'm Marcos. I'm from Brazil originally, so it's nice to be back here. Since the beginning of this year, I moved to the University of Groningen as an assistant professor. But now the things that I'm going to show you were done at during my postdoc at Cornell with Professor Dan Ralph, and in Eindhoven with Professor Bert Koopmans. And I have to thank a lot Dave McNeil and Greg Steele, which were the people that actually started with me the field on a spin-orbit torques using multi-layered layered materials. And a PhD student from Eindhoven that continued working with me there on a spin-orbit torque with layered materials. And the work that I'm going to present for you today is basically is very experimental, so it's going to be very more hand-wavy kind of explanation. But I'm going to use symmetries to try to explain how the symmetries of the system actually can give you a huge impact on the spin-orbit torques that you measure in the devices. So we'll give a short introduction to what spin-orbit torques are, and then I'll move into devices based on layered materials, and specifically on tungsten telluride, then niobium diselenide, and finally, hopefully, it can show you some new results on nickel thio-phosphate. So why should we care? I think all of you are here and you know that we should care about spin electronics, but the spin torques specifically are coming into market into spin transfer torque magnetic random access memories, and they use a basic concept of tunneling magnetoresistance as we use in the old hard drives, right, from computers, not the solid-state drives, in which you have a fixed layer, you have a barrier, and then you have a free layer, free magnetic layer that can switch direction, right? So this you can encode bits 0 and 1. And the way to switch these bits is by driving a current through, and by spin transfer torque, then you can switch the magnetization of the free layer. But there is a problem there, is that these barriers are pretty sensitive, pretty difficult to make, and you blast it with a current, so every now and then they blow up. So nowadays, the next generation and people at IMAC are working hard on to doing that in wafer scale, which is using a spin-orbit torque magnetic random access memories, in which we have a write line. So we have, in order to write the bit, we don't drive the current through the tunneling structure, but we pass a current through a write line, and due to, for example, a spin Hall effect, in which spins that point in different directions go to opposite directions in your device, then they can apply a torque in this free layer, and you can actually switch the magnetization. So it's has been shown to be much more effective way of doing so too. And we can quantify the effectiveness of these systems by the spin Hall efficiency or spin Hall angle, which is the constant that will relate the generated spin current to the applied charge current. So we want a very large spin Hall angle to get a very large spin current, so we can switch these ferromagnets very effectively. And for that, we need a very high spin-orbit coupling in the material that consists of a write line to get a very large spin Hall effect. Right? But as I'm going to show you, the symmetries of the write line actually do affect the properties and the types of torques that you can apply. So sometimes also playing with the symmetries will give you an extra knob to tune these effects. So why do I want to use layered materials? Well, it's a very large family, so I can choose of many different properties, resistivity, band gap, and crystal symmetries. They're very easy to exfoliate, so I just go to the staples, buy a Scotch tape, and then I can exfoliate my crystals. And they're atomically flat and single crystals, and this is very important for what we do, because if we want to look at the symmetries on the impact of the symmetries on the spin-orbit torque, we want a single crystal. And they can show a very, very high spin-orbit coupling. So in principle, they should be very good to be used for spin-orbit torques. Okay, so how do we measure? I'll go very fast about that, of what spin-orbit torque is and how we measure it. So if we have the spin-orbit material in contact with a ferromagnet, the ferromagnet has a certain magnetization M pointing in a random direction over there. If we drive a current through this spin-orbit material, this current generates a magnetic field, which I'll call the Ørsted field. And this Ørsted field applies a torque on the magnetization that points out of plane. So the magnetization wants to move out of plane because of precession. And if you write down the mathematical equation for that, the torque is an out-of-plane torque, and it has a product of the direction of the magnetization M cross y. So y is this direction perpendicular to the parallel to the plane here. So this could be due to an Ørsted field, or it could be due to some other spin-orbit type effect. So this is a field-like torque, right, which is odd in the magnetization direction. And now if you have, for example, a spin-Hall effect, so I'm injecting spins pointing in the y direction into my ferromagnet, this will cause an in-plane torque, which has a symmetry of M cross Y, which is even in a magnetization direction. And this could be due to a spin-Hall effect, for example, in bulk materials. This could be due to a Rashba-Edelstein effect. So it's a Rashba spin-orbit coupling at the interface between my spin-orbit material and my ferromagnet. And this I'll call the anti-damping-like torque, so an even torque in the magnetization. And we measure this. All the techniques that we use are based on AMRs, which means that the current, so we're driving a current, and we have the magnetization in our ferromagnet, and the resistance that we measure is proportional to the angle that the magnetization makes with the current. So if we change the angle of the magnetization because of spin-orbit torque, for example, then we will see a change in the resistance. Right? And one technique that we use a lot, which was originally developed at Cornell and Dan Ralph's group, is spin torque ferromagnetic resonance, which is a ferromagnetic resonance technique that we have a coplanar waveguide for radio frequency currents. We send a radio frequency current through this coplanar waveguide, and between the signal line and the ground line, we have our little teeny tiny spin orbit metal ferromagnet bilayer. So that's the thing that we're interested in measuring. And let's say that we send a 9 gigahertz current, and we sweep the magnetic field, and when the Larmor precession frequency of the ferromagnet matches the frequency of the current, then we have a resonance condition. And this resonance condition causes a DC voltage on this device that we can detect via a lock-in amplifier, and we get a signal as a function, so the DC voltage is a function of magnetic field. So when we reach the Larmor precession frequency of the ferromagnet, we get this resonance peak. And this resonance peak can be separated into two components, a symmetric Lorentzian and an antisymmetric Lorentzian, so it's basically one plus the other. And it turns out that the antisymmetric Lorentzian, it's proportional to, well, a bunch of terms times the torques that point out of plane. And the symmetric Lorentzian is proportional to the torques that point in the plane of the device. So if I assume that the out-of-plane torques are just to the Ørsted field, which is proportional to the current, and this in-plane torque is just proportional to the spin-Hall effect, for example, if I divide one over the other, I get something that's proportional to my spin-Hall efficiency, right? So that's why it's so easy, in principle, to extract this value. I'm doing a little bit simplified over here. It's a little bit more complicated than that, but that's the spirit of it. Okay, so I told you that I would like to talk about the symmetries of the right line, so the symmetries of my spin-orbit metal. So let's take a stereotypical device, which is platinum permalloy, and let's look at the symmetries as I reverse the magnetic field. So I have the magnetic field pointing here at 40 degrees, magnetization follows the field, and I will do 40 degrees plus 180, so reverse the field to the other direction, and I plot the STFMR results on top of each other, and they nicely follow on top of each other, exactly like what you would expect if you have, for example, mirror symmetry or inversion symmetry or so on and so forth. But now if we do that for tungsten ditelluride, so we have, instead of platinum, we have tungsten ditelluride, we apply the field in one direction, reverse the field. If we check the results, they're very, very different. And in principle, that in the beginning, this was very puzzling, and especially because it's a type of torque, it's an M cross Z, so it's an out-of-plane anti-damping torque, which turns out that is the nicest type of torque, so the ideal torque to switch out-of-plane magnetic devices. And so this means that is a much more efficient way instead of switching for a spin Hall effect, for example. But why is it there? Actually, the microscopic mechanisms we don't know, but I can give you some symmetry considerations on that. So if you look at the tungsten telluride symmetries at the interface, we're looking the crystal from the tungsten telluride crystal here from the top. We have a mirror plane along the B-axis of the crystal, and if we're flowing a current along this mirror plane, so parallel to the mirror plane, and this current, all the torques that we're measuring here, they have to be linearly proportional to the current, right? So it's apply the current, I measure a torque that points out of plane, right? And if I apply this mirror plane, the current doesn't reverse sign, so the current points in the same direction, but the torque is a pseudo vector, which means that if I apply the mirror plane, the torque reverses sign. So this means that my current points in the same direction, but my torque reverses sign, so it has to be zero by symmetry, right? But what if I flow the current now perpendicular to this mirror plane, and then now I have that the mirror plane will reverse the current direction, but also reverse the torque. So symmetry considerations will just tell you that, that's okay, that's allowed. Right, and then it turns out that if you make many devices with the current pointing in different directions with respect to the mirror plane, you can see that if we are pointing so that we have the torque, this out-of-plane anti-damping torque as a function of the angle to the a-axis, so the angle perpendicular to the mirror plane, that we have a maximum when the current flows along the a-axis, and it nicely decreases as it goes parallel to the mirror plane. So it seems to be coming really from the symmetries of the tungsten telluride. And an effect, well, similar to that was recently measured by the MIT group and the Cornell group, Pablo Herrero and Kim Mak, and it was published earlier this year in Nature Materials. Although they still don't know very well what the microscopic mechanisms are, so it's still a lot of debate there. But how does it size up against platinum, for example? So platinum, we have a very high efficiency, but tungsten telluride still lagging an order of magnitude behind. And well, this partially has to do with the fact that tungsten telluride is pretty resistive, but at least, well, it's pointing us in the right direction, right? So what about we go metallic then? So we started with tungsten telluride, which is orthorhombic material and semi-metallic. Now we move to niobium diselenide, which is hexagonal and metallic. And the hexagonal, well, it's a higher symmetry. It has a C3 rotation along the z-axis. So we would expect that these weird torques that are allowed in tungsten telluride to be absent there. But at least you have a very high spin-orbit coupling, higher than tungsten telluride, and you have a much higher conductivity. So we play the same trick. We make our devices, our STFMR devices, and we have niobium diselenide with a ferromagnet on top, and we nicely measure these resonance curves down to a monolayer of tungsten diselenide. But now if you reverse the field direction, we see that they look very, very different, which in principle is actually not allowed by symmetry. So that is actually very puzzling. And for that, we just did a series of devices with different thicknesses. And if you look at the field-like torque, which would be coming from, for example, Oersted fields flowing through the niobium diselenide, versus niobium diselenide thickness, they nicely fall into a linear behavior, right? So exactly what you would expect from a current flowing in niobium diselenide. So far, so good. We now go to the anti-damping-like torque, so spin Hall-like or Rasch-Edelstein-like if it's an interfacial torque. And the behavior is not very, very clear. And moreover, if we have just a single niobium diselenide layer, you already measure a torque. So this can't be due to a spin Hall effect, for example. It has to be an interfacial torque. You could have an extra contribution there, so things start getting more complicated. But now if we follow this weird torque, which is a field-like torque, it turns out that's an M cross Z if you do the full angular dependence. As a function of the niobium diselenide thickness, it's all over the place. Sometimes it's 0, sometimes it's negative, sometimes it's positive, so it doesn't make any sense. And the only way that we could actually explain this is if we take our niobium diselenide, we're now looking at the top view, and the only way that this torque can appear is if we take, so now the torque would be 0 by symmetry, but if we stretch it, then symmetry allows it. So that's the only way that a symmetry could allow a torque like that to appear. If we break some symmetries of the crystal, specifically the C3. So if this is true, which we can't control in our experiments, we think that this strain is just coming from the ferromagnetic layer that's on top, that is straining a little bit our crystal, and it strains sometimes a lot, sometimes a little bit, sometimes in a different crystallographic direction, so that's why it's all over the place. But if this is true, we can envision a device that we can controllably break the symmetry by using a piezoelectric, for example, that we tune the torque intensity and we turn it on and off, right? Which is very nice. But there is another way, another knob that we can turn, which is actually much easier to make, which has to do with a phase transition in the material. And now I switch into going to antiferromagnets, because then you can tune the symmetries by just changing the temperature. Right? So you go above the transition temperature, you have certain symmetry. When you go below, you break some symmetries because of the antiferromagnetic order. Sure.
So in your previous slide again, are you going to show some results on this, or this is just a gas and then you're going to show something else now?
That's just the gas.
Okay,
so I would like to do a strain-controlled experiment, but it turns out that it's pretty difficult for many different reasons.
But even at the qualitative level, like intuitively, can you somehow explain a little bit why is it all over the place? Is it consistent with some kind of hand waving type of view of the strain, whether it's compressive or not?
So we can't. The problem is we can't control anything in this. So what I can tell you is that for the same fabrication run, you have many points here which lie sometimes negative, sometimes 0, sometimes positive. They are different flakes, and we have to go through a very complicated sample fabrication process. So the strain from device to device can very well be different. Can be in different directions. Can be compressive or cannot be there. So it's difficult.
I also have a question. If you fix the number of layers and you do several experiments, do you also see this variation?
Yeah, so if you look here, I mean, this is the thickness measured by atomic force microscopy. So it's, and then we just divide by the interlayer spacing. We have the niobium diselenide layers. If you look, for example, here, we have two devices that have very similar number of layers, but it seems to be pointing this different direction. Right, so even if you go like one layer below, one layer above, doesn't seem to be any correlation there. So that's why we're guessing that is because of strain caused by the ferromagnetic layer. Okay, so now I decided to try on antiferromagnets because they're a nice way to tune the crystal symmetries by temperature. And specifically, there's a family of layered antiferromagnets called metal thiophosphates, the chemical formula metal phosphorus sulfur 3. So specifically here, we're going to look at nickel thiophosphate that are nicely exfoliatable, and you can do a lot of stuff. They have a very large band gap. So semiconductors here, well, it's basically an insulator for all purposes. They're a little bit air unstable, but that's okay. But the new temperatures are nice and convenient of hundreds or hundreds of kelvins. So nickel thiophosphate is about 170 Kelvin. And now, if you look at the crystal symmetries, so if you have a bulk material, is crystal, the symmetry group is C2/M. But if you look at the monolayer, is a D3H. The important part here are these mirror planes that you can see the 3 mirror planes over there. And now if you go below the neo-transition temperature, you induce magnetic ordering in this material. And nickel thiophosphate is a nice zigzag lines. So you break 2 of these mirror planes and you're left with just 1, exactly like what we had for tungsten ditelluride. Right? So it's pretty nice. And then we reduce the symmetry to a PM or a CS. Okay, so let's see how they look like. This we are measuring with a little bit different technique, but we can extract the torques nonetheless. So if you look at the field-like torque, so the one that would be coming from the Ørsted fields, however, here there's a catch. There's no current going through the nickel thiophosphate because it's an insulator. So all the torques that we measure here have to be interfacial torques. So it has to arise from the interface between our layered material and the permalloy, right? Now we flow the current along a certain direction, and we have this torque, this field-like torque as a function of temperature, and you can see that at room temperature, and the scale here is more negative going down, so the torques are in the negative side. So as we cool down, they seem to be increasing in magnitude and saturating along a certain value. Now if we change the current direction, so that we apply the current 90 degrees with respect to the initial part, we see that it's slightly different. So it's slightly higher in magnitude. And this we could understand more or less if we have our current going in a certain direction, which makes an angle with this mirror plane. And now if we flow the current 90 degrees from the initial current, then the angle with the mirror plane changes. So in principle, we expect a different magnitude for the torque. The more striking result is for an anti-damping-like torque, which is coming from, for example, Rasch by Edelstein. It's an interfacial torque. That if we look at the anti-damping-like torque as a function of temperature, we start right there very comparable to devices made of tantalum permalloy or platinum permalloy, which are the standard in the field of spin-orbit torques nowadays. And it you can see a slight increase there. The transition temperature is somewhere around here, 170 Kelvin. But now if we flow the current in a 9 degrees rotated, we see a very different behavior. And it's a 7-fold increase as compared to a tantalum permalloy device. And it looks like it starts over here. It has some transition, and over there there's some saturation. But of course, that I'm squinting my eyes like that to see what I would like to. Why this happens, we have absolutely no idea. And why is it strong? We also have absolutely no idea. Because nickel, phosphorus, and sulfur are relatively light materials, so we would expect a very small spin-orbit coupling. But surprisingly enough, we measure a very large spin-orbit torque. We didn't see a very strong behavior as we go through the Neo temperature transition, which could be due to that even at room temperature, you can have some local magnetic ordering for nickel thiophosphate. You actually can measure that by Raman, that we can see a magnon peak even at room temperature, albeit very, very low. As you go through the Neo temperature, it really develops very nicely. And then you get a long-range order. But apparently, the spin-orbit torques don't care too much about that. So I'll just summarize. That's my last slide. So what we know so far from these three materials that we studied compared to platinum. So platinum, we have a nice anti-damping spring Hall-like torque, but the out-of-plane anti-damping torque and the field-like in-plane torque are not allowed by symmetry, and we don't see them. So that's good. The tungsten telluride, we allow all these three type of torques, but we only observe one of them. It's very unclear, actually, why that's the case. And for the niobium diselenide, that's the same thing, that if we strain it, we in principle allow for all sorts of torque to appear, but we only observe the field-like in-plane torque. Why this is the case, we also don't know. And the nickel thiophosphate, where we also allow below the Neo transition temperature, we only observe a very large anti-damping-like torque, which arise at the surface because it's an insulating material, but where it's coming from, we also don't know. So to summarize, we need to get better understanding on that, and so we have to push the theoreticians to do a lot of work on this to actually tell me where they're coming from, so we can actually do more nice work there in spin-orbit torques. So I would like to thank you and welcome any questions.
Thank you, Marcos. We already have a question here from Agus.
So this last point, then where you go over the phase transition, do you think that it's actually a finite size effect, that you don't really have a fully developed phase transition? Is that what you mentioned when you said it's not really diverging? Or